This module will look at how students will come to understand addition and subtraction in early years, and then we'll focus on how students develop more formal and efficient strategies for subtraction. And then there will be two following videos. One will continue that line of thought, and then the other will take a look into how this understanding extends into algebra. Let's review the CGI as it relates to subtraction progression. This module will take a deeper dive into CGI, thinking about the difficulty with problem types and the models used for representations. Writing problems and determining problem types is a key activity for teachers K-3 as students build their understanding of number and become more fluent with addition and subtraction problems. Then we'll focus on subtraction contexts, models, and strategies. Pause here to identify the problem types for these four problems. You can find these in your pause and play document. You'll probably want to refer back to your notes from the previous module. Once you've completed the task, press play to resume. The first problem is a separate result unknown because there is an action of taking away and the result is the unknown component. The second problem is a separate start unknown. Like problem 1, it also has a removing action. He gave the candy to his sister, but this time the initial amount is what's missing. The third problem is a compare quantity unknown. We know one of the elements being compared and how much larger it is than the other element. This is considered a static or no action situation because the difference does not come about because of joining or separating action. Lastly, number 4 is a part whole, part unknown, because we're looking at a set of crayons and looking for one of the parts of that set. Pause here and see if you can take a minute. Try to rank them in the order in terms of difficulty. What do you think would be the more difficult ones for students to try and why? Given a child's developmental stage, direct modeling, counting, derived facts, some of the CGI problems are easier to solve than others due to certain characteristics. One example is whether or not the problem involves action. Children's early problem-solving strategies mimic the action in the context. The join to and separate from problem types involve physical actions which can be modeled. Children can imagine joining and separating quantities by acting out the context. Direct modelers are typically able to solve join and separate result unknown problems because they can act them out with physical objects. The part whole and comparison problems are static. No action is involved. These problem types describe a conceptual bringing together or comparing quantities, which is not as easy to act out or model. The problem types which involve action are not all equal in difficulty due to their structure. A join result unknown is easier than a join change unknown, and a join change unknown is easier than a join start unknown. Start unknown problems are challenging because these problems, though they involve a physical action, are really hard to act out. Students don't have a starting place as a beginning, so they tend to use a trial and error approach to solving these problems. Comparison problems use language that can be complex for young children. Fewer, less than, more, bigger, and greater are terms used to compare quantities. Students tend to have more experiences with bigger and more. It's important that they also have experiences with finding fewer and less than. Teachers who see the compare problems as trick questions need to realize that students use models or number sets can solve these without using keyword strategies. Number sets can also make a problem more difficult. Sometimes teachers use different options for number sets as a way to differentiate for student needs and abilities. In this problem, Jessica can have 10 toy cars and lose 3 of them, or she could have 23 toy cars and lose 14 of them. To review, this chart shows the progression of difficulty. Green are easy. These are the ones you find in the kindergarten standards. Blue are moderate. Young children will find these difficult. Orange are more difficult. When we change certain words, they're challenging. And yellow are the most difficult for young students and can challenge older elementary students as well. In thinking about the previous problems, the order is separate, result unknown. So Jessica and the toy card problems, that's going to be the easiest. Then the crayons problem, it's a part whole. And then the chess club problem is a compare. And then the separate start unknown, that's Ryan with the candy. That's your progression in difficulty. By the end of second grade, students are all expected to be able to reason through all of these types of problems. As we assess a student's ability to solve a problem, we should consider the problem type, number sets, tools, and students' developmental level. Writing problems and determining problem types is a key activity for K-3 teachers as students build their understanding of number and become more fluent with addition and subtraction problems. For fourth grade and beyond, cognitively guided instruction can teach us about how a given context will drive and motivate student strategies. This is especially true when students do not have a known algorithm yet. Throughout this and the next few modules, we'll see how we can pose problems in ways that highlight certain concepts. Eventually, we want students to develop and use efficient algorithms, but we need to connect those to students' less formal thinking. Two more notes on CGI. First, the problem types are not the same as the keyword replacement we see in some curricula. CGI is about students actually making sense of context and using manipulatives, pictures, symbols to represent and solve the problems. When students memorize keywords and replace them with symbols, they are relying on procedures that stop working in later grades as problems become more complex. Second, again, the names of the problem types are for teachers to know, not students. As teachers, we want to make sure students are getting a variety of problem types, but they don't need to know their names to be successful. Pause here. How do you represent the quantities in this problem using counters or bars? Plus, press play when you're ready to resume. Providing students with representational tools can help them develop confidence to tackle a problem. A powerful tool is the bar model because it helps students visualize the relationships between the quantities in all problem types. Students can use the bar model to explain their reasoning and determine solution methods. For students to progress through the representations, help them make connections between physical objects such as counters to visual marked bar models, and then to unmarked bar models. Making connections between the visual representations and symbols, such as numerals and signs, strengthens their understanding of what is happening in the equation. Pause here, draw a bar model representation for each of the contexts. What is known and what is unknown. Press play when you're ready to resume. Using a bar model to represent the problem highlights the part-whole relationship specified in the context. The representation helps students choose an operation rather than guessing at a solution method. Through questioning, students can make connections between the equations and the representations, which helps students understand that they can use different computations to solve the problems. For example, in the soccer team situation, a student can use subtraction, 13 minus 8, or addition, what do I add to 8 to get 13? Bar modeling is very helpful in comparison situations where the language is more complex. Here you can see that the bar model represents the two sets and their differences. We can clearly see what quantity is known and what is unknown, or what the numbers 8 and 5 and 3 refer to in each situation. Again, students can make connections between the representations and the solution methods and begin to see the relationship between addition and subtraction. In general, modeling a problem encourages problem solving to become a sense-making activity, a way to determine the meaning of a situation and the quantities involved. Strategies are purposeful and solutions are sensible. Pause here to consider these questions. Press play when you're ready to go. To get us started, pause here and do these two problems. Assume you are a student who does not yet have a traditional algorithm for subtraction. First, determine the problem types. As you work, consider how do the context drive your solution strategies? How are your solution strategies different and what models are you using? Press play when you're ready to continue. So you've noticed that the two problems are different. The almond problem is a separate result unknown, and the plant problem is a join change unknown. Though both situations involve a missing part, these are examples of how we can use context to press for certain concepts, and how different contexts might generate different models within a classroom. Let's see where each of these contexts could take students by looking at the use of different models and the different strategies for each context. Note on the following this, I've labeled models in red and strategies in blue just to help you see the difference. The strategy is the mathematical reasoning and the model is a representation. The first context about eating almonds is a takeaway or removal problem. The context suggests a certain strategy. Students will often tend to start by using manipulative pictures or something like tallies to represent the initial number of almonds and then take away or remove the number eaten. Take a moment to pause and study these models, then click play when you're ready to continue. We can guide students to use base 10 blocks to represent the situation. The first situation or solution shows a model of 43 using base 10 columns and cubes. 10 is taken away, then 7 is taken away. That leaves 20 plus 3 plus 3. More cube, or 3 plus 3 more cubes. So 43 take away 17 is 26. I took the 17 based on place value, 110 and then 7 ones. One thing that's interesting about this is what children without an algorithm often do is that they sort of use place value, but in a way that does not require them to borrow and regroup, as I talked about in the previous video. This can be really powerful. The second solution shows the strategy jumping using friendly numbers on the number line. I start with 43 and remove 10, that's a friendly jump, to land on 33. And then I jump back 3 to get 30, also a friendly number, and then I jump the 4 to get to 26. So my jumps in total are 17. If these models and strategies were used by my students, here are some follow-up questions I might pose. Can you compare the use of the models? Where do you see 17 in both models? What is similar? What's different? Here are some additional models and strategies. The first solution shows the strategy compensation using an open number line. Compensation is changing one number to a friendly number, performing the operation, and then adjusting it back to compensate for the original change. So here, I changed 17 to 20 to make it an easier problem. I subtracted 20 from 43, which gives me 23. Yet I have to adjust my 23. Because I took 3 more than needed, I have to add that back, which results in 26. This can be a really great mental math strategy. Next, I use counting down using arrow language. This model is a model that, again, comes from a number line. It's just a more abstract form. I've used arrows to represent the jumps on a number line. It's a good example of how I'm using the same strategy as the one I used previously, but using 2 different models. So let's look at the tree diagram. I'm going to get rid of my marks on the screen here. The tree diagram is one that students usually can use informally to break the numbers apart. This student's able to use what looks to be negative numbers. They might be using negative numbers, or they might be using this idea of, I still need to take away. In this problem, we start with 40 minus 10 is 30. I can take 3 away from 3, but I will still need to take away 4 more in order to take away a total of 7. That leaves me with 30 take away 4. The result is 26. The partial differences is just a different way of setting up the same thing and is commonly used in many countries. Again, we can think of the minus 4 as I still need to take away. They're not officially thinking in terms of negative numbers yet, but I still need to take away. By starting with the largest place value, we easily take away 10 from 40 to get 30. And then realizing that 3 minus 7 means I have to take away 4 more, I get 26. Now let's look at the plant problem. In this context, we're thinking about how much more the plant has to grow. Instead of removing a number, we are emphasizing subtraction as the distance or the difference between two numbers. In this case, we're looking for the distance between 17 and 43, which can be represented using either a subtraction or addition equation. The addition equation leads to the strategy of counting on. Take a minute to look at the models and strategies here. Where is the answer in each representation? In the first example, using the base 10 blocks, I add 26 blocks to 17 to get 43. In the takeaway model, the answer is on the number line. In the distance model, the answer is between the numbers. I start at 17, jump by 3 to 20, then I jump by 20 to 40, and finally by 3 to 43. My answer is the total jumps, 26. This is a good example of using the same model, but a very different strategy as we used in the almond problem. First, we see on this one the arrow language model showing jumping from 17 to 43. Notice that the answer to the problem, 26, is the total in jumps, 10 plus 10 plus 3 plus 3. If needed, take a moment to compare between this arrow language model and the one on slide 21. Because we are looking at distance between two numbers, here we can shift the numbers to ones that are more easily operated with as long as that distance stays the same. This is known as a shift strategy. In this case, if we add 3 to both numbers, we can look at the distance between 20 and 46, which is much easier to calculate. This is another strategy helpful for mental math. The idea that subtraction can mean distance ends up being key in algebra and geometry. In solving both contextual problems, we see how we use different strategies and models to determine a solution to a subtraction problem. We also see how the context drives the strategies and models we choose to use. Between the two subtraction contexts, we used strategies such as removing, counting on, decomposing, both numbers by place value, compensation, and the shift strategy. The models used progress from physical to visual to symbolic. It's interesting to note that students might use the same model, yet use a different strategy, or they might use the same strategy in different models. When students discuss the similarities and differences in the use of strategies and models, they make really rich connections and their conceptual understanding of the topic deepens. Hopefully you are taking away some key ideas. CGI is about students actually making sense of context and using manipulatives, pictures and symbols to represent and solve problems. The ultimate goal of CGI is to help children build upon and extend intuitive modeling skills that they apply to solving problems. As students experience representing and solving these addition and subtraction problem types, which are rooted in part-whole relationships, they'll gain a deeper understanding of the inverse relationship between addition and subtraction. And as student strategies progress in sophistication, they will become more flexible and efficient. While problem types drive certain strategies early on, in time, students will begin to use strategies that are not consistent with the problem structure or action. This will serve them well as they face more challenging problems in later grades. To get us started, pause here and do these two problems. Assume you're a student who does not yet have a traditional algorithm for subtraction. As you work, how do the contexts drive your solution strategies? How are your solution strategies different? So hit pause and then try to reason through these problems, and then when you're ready, hit play. So you have noticed that the two problems are a little different. The first context about buying books was more of a takeaway problem. Students will often tend to start by using manipulatives or pictures or something like tallies to represent the initial amount and then take away the amount spent. We've shown that here with hundreds blocks. You started with 200s, which are the flats, and 5 unit cubes. Taking away 4 of the unit cubes from one of the hundreds flats leaves us with 96 units that we can now take away completely. So if we combine the 4 units from the first hundreds cubes and the remaining flat units, Bernice will have a total of $109 left. Now, the second context about the road trip emphasizes subtraction as a distance. In this case, we're looking for the distance between 96 and 205. Students tend to draw a line if they need a visual for this problem. This student was fairly efficient in making their jumps from 96 and up at 205. In less efficient thinking, we might see more jumps to get to 205. This is an example of how we can use concepts and how different contexts might generate different models within a classroom. Let's see where each of these contexts could take the students. To also bring it back to the conversation of strategies and models, take a look at the books problem. The strategy is taking away, and the model is the base 10 blocks. In the road trip, the strategy is adding up to find the distance, and the open number line is the model. The takeaway context of buying books problem can lead to several key ideas. We've talked about using direct modeling or base 10 blocks. We would want to press students to represent that process symbolically, as shown here. Take a minute to pause and connect the base 10 blocks to the symbolic notation. So look down here. Where do we see that this is representing what's happening in our model? Hit pause when you're ready to go on. One interesting note, children often naturally use place value, but in a way that doesn't require them to borrow or regroup. This can be really powerful, especially when doing mental math. This problem can also be represented on a number line, even though the context may not press students to draw on a line. We can think of starting at 205 and then taking away and jumping back until we've taken away 96 units. Some of you may have compensated to solve this problem mentally, meaning you took away more than you needed to, but then added it back in the end. In this case, we can do 205 minus 100 and then jump back the 4 that we needed. The number line is also helpful for seeing how this works. Let's take a look at the road trip problem. Rather than starting at 205 and subtracting 96, most people look at the distance between the numbers. Take a moment to compare what we did here with what we just did. Where is the answer in each representation? In the takeaway model, the answer is on the number line. In the distance model, the answer is the distance between the numbers. This idea that subtraction can mean distance ends up being a key idea in algebra and geometry. It's how we count back change, or should be counting back change. In the bottom model, we've used arrows to represent the jumps on a number line. This is called arrow language and can be a convenient shorthand. This is a good example where the strategy is the same, but we're using 2 different models to represent the strategy. Because we're looking at distance here, we can shift to numbers that are more easily operated with as long as the distance stays the same. In this case, if we add 4 to both numbers, we can look at the distance between 100 and 209, which is really a lot easier to calculate. Eventually, we want students to develop efficient algorithms. The standards press all students to have a place value-based subtraction algorithm by 4th grade. Informally, students often use something like a tree diagram. So we're going to look at this one right here. They look at the tree diagrams to represent taking away by place value. So this student might be using negative numbers or the idea of, I still need to take away. If we start with the largest place value, we start with the hundreds, so it's 200 minus 0. Then there are 0 tens here, but in the 205. But I still want to take 90 away. So if I take 90 away from 200, I get 110. Now I can look at that 5 and I can take away 6 from that 5, but I still have one more to take away. Do you follow me on that? I said it deliberately. I take 6 away from that 5, so I can take away 5 of those, but I still have one more to take away. This is easier to see with place value blocks. 200 minus 0 is 200. Then I want to take away 9 tens. I don't have any tens to take away, so instead I take 9 tens from the 200 I have so far. So I would, it's not here, so I would cross out basically 9 tens, and I would have one column here that's still left. Lastly, I need to take away 6 ones, so I can take away those 5, but I still have one more that I need to take away, so I'm going to take it away down here. So now I have my 100 and then my 9 that's right there. Partial differences is a different way of setting up the same thing and is commonly used in many other countries. Again, we can think of the minus 90 and minus 1 as negatives, or I still need to take this away. By starting with the largest place value, we can take away 90 from 200 to get 110, and then take away 1 to get to 109. The traditional algorithm is more compact. Rather than using negative numbers or the still need to take away idea, we use decompose by place value. We commonly say that we can't take 6 away from 5, so we go to the tens place to take a 10 that we can give to the 5. In this case, we have to go to the hundreds place. Take 100 from 200, leaving a 100. Decompose that 100 into 10 tens and leave 9 of those tens in the tens place. Now I can give 110 to the 5 to create 15. At long last, I can do 15 minus 6 to get 9. 9 tens minus 9 tens is 0 tens. And 100 minus 0 is 100. Sometimes this is expanded out so students can better track the place values. While this algorithm is very compact, it tends to mask really difficult concepts like place value in the interest of efficiency. And there are times when efficiency is our goal, but we should stress that when our students operate procedurally without considering place value, they're no longer building number sense. They're simply acting as a human calculator. In solving both contextual problems, we see how we can use different strategies and models to determine a solution to a subtraction problem. We also see how the context drives the strategies and models we choose to use. Between the two subtraction contexts, between the two that we used, strategies such as removing, counting on, decomposing both numbers by place value, and compensation. The models used progress from physical to visual to symbolic. It's interesting to note that students might use the same model yet use different strategies, or they might use the same strategies and yet different models. When students discuss the similarities and differences in the use of strategies and models, they make rich connections and their conceptual understanding of the topic deepens.